Max Planck's life began in a Germany still clinging to rhythms reminiscent of the medieval era, yet simultaneously racing headlong into modernity. He was born in 1858 in Kiel, a tranquil port city nestled by the Baltic Sea, into a family where scholarship wasn't merely a badge of honor, but a deeply ingrained tradition. His father was a law professor, and his mother hailed from a lineage of theologians and academics. Their household fostered an atmosphere of serenity, structure, and profound respect for learning. Within this environment, young Max absorbed the conviction that truth mattered above all else, that ideas possessed genuine moral weight, and that discipline itself held a certain intrinsic beauty. When Planck was 9, his family relocated to Munich. The city broadened his horizons, exposing him to magnificent churches, a vibrant cultural scene, and schools that nurtured Germany's burgeoning professional class. He demonstrated talent in nearly every field, particularly languages and music. He played the piano with remarkable subtlety, and even entertained fleeting aspirations of becoming a musician. Even later in life, after achieving global recognition as one of the foremost physicists, he would confess that music remained his cherished private sanctuary. The way he contemplated harmony and structure in music would subtly influence his approach to unraveling the hidden harmonies of nature. At the Maximilians Gymnasium, his teachers swiftly recognized his intellect as both exceptionally sharp and remarkably well-balanced. He didn't seek fleeting glory through ostentatious displays. Instead, he was thorough, meticulous, and undeterred by tackling complex, protracted problems. One teacher, Hermann Müller, played a pivotal role in introducing him to the principles of energy conservation and the burgeoning field of thermodynamics. Planck was immediately captivated by the notion that the universe might be governed by universal principles, immutable laws so profound that they remained impervious to opinion or passing trends. This unwavering attraction to fundamental laws would form the very bedrock of his scientific endeavors. In 1874, at the age of 16, Planck enrolled at the University of Munich to pursue the study of physics. At the time, it was a field still in the process of defining itself. Newtonian mechanics held absolute sway. Thermodynamics was a relatively nascent discipline. The existence of the atom was still subject to debate in certain circles, and the term quantum had yet to enter the scientific lexicon. Planck attended lectures delivered by two intellectual giants. Philip von Jolly and the spirit of Ludwig Boltzmann hovered nearby, even though Boltzmann himself wasn't physically present in Munich. Jolly, a conservative and skeptical figure, cautioned Planck against pursuing physics, suggesting that nearly all worthwhile discoveries had already been made. While many young minds might have interpreted this as a discouraging sign, Planck viewed it as a challenge. If physics was nearing completion, he reasoned, then its most profound foundations must be within reach, and he was determined to comprehend them. He continued his studies in Berlin in 1877, attending lectures by the legendary Gustav Kirchhoff and Hermann von Helmholtz. Berlin at that time served as Germany's intellectual crucible, characterized by intense competition and innovation. Yet Planck was not easily intimidated by brilliance. He prioritized clarity over fame, drawn more to the quiet elegance of a correct equation than the fleeting applause of a seminar audience. He discovered a profound philosophical satisfaction in thermodynamics. Unlike the mechanics of motion, thermodynamics grapple with direction, irreversibility, and the perplexing reality that time seemed to possess an intrinsic arrow. It probed the underlying reasons why heat flows in a single direction and why systems naturally tend towards equilibrium. Planck sensed that these questions hinted at something almost metaphysical, a lawfulness that touched upon the very essence of order itself. In 1879, he completed his doctoral dissertation on the second law of thermodynamics. This was not a trendy subject, nor did it promise immediate recognition. But Planck was not a man driven by trends. He was already wrestling with the question that would preoccupy him for decades to come. What is the underlying basis for the truth of the second law? Is it merely statistical in nature, as Boltzmann contended, or does it represent an absolute law of nature? Planck leaned towards the notion of absolutes. He sought certainty, not mere probability. He was the kind of scientist who perceived the universe as fundamentally rational and felt uneasy with the idea that its laws were simply descriptions of average behaviors. After earning his doctorate, Planck navigated the traditional German academic path. He became a Privatdozent in Munich, then secured a position as an associate professor in Kiel, and later moved to Berlin, where he would spend the most significant portion of his career. These were years marked by consistent, diligent work rather than spectacular breakthroughs. Planck authored papers on thermodynamic equilibrium, entropy, chemical reactions, and the very foundations of physical law. He married Marie Merck in 1887, and their relationship brought warmth and companionship to his otherwise disciplined existence. Their home was a sanctuary of music and intellectual discourse, a place where the private man and the public scholar could harmoniously coexist. By the early 1890s, Planck had attained a stable position as a professor in Berlin. While many physicists in his situation might have felt a sense of arrival, Planck experienced something different. He remained driven by the search for the fundamental law he believed lay concealed beneath thermodynamics. Furthermore, the world around him was undergoing rapid transformation. Electricity and magnetism were being unified through Maxwell's equations. Experiments involving radiation hinted at enigmas that classical physics couldn't fully resolve. A new brand of physics was emerging at the fringes, though most scientists were yet to fully grasp its implications. Planck's entry into this impending storm occurred through what initially appeared to be a narrow, technical problem. Both industry and science were increasingly interested in blackbody radiation, the way hot objects emit light. The problem held significance for both theoretical understanding and practical applications, ranging from furnaces to the burgeoning field of electrical lighting. Experimentalists had diligently measured the spectrum of blackbody radiation with ever-increasing precision, but theory lagged far behind. Classical physicists had developed formulas that only worked effectively within limited ranges. At low frequencies, the approach devised by Rayleigh and Jeans provided a good fit. At high frequencies, Wien's law aligned well with the data. However, no single equation could accurately capture the entire curve. Worse still, the classical prediction at high frequencies led to an absurd conclusion. The energy should escalate infinitely, a catastrophe that would later be dubbed the ultraviolet catastrophe. Nature, however, resolutely defied this prediction. Something was fundamentally amiss within the theoretical framework. Planck did not simply stumble upon this problem by chance. He was invited to lecture on heat radiation, and as he prepared, he became utterly absorbed. He approached it as a thermodynamic puzzle. If radiation existed in equilibrium with matter, then its energy distribution should adhere to a law that was consistent with entropy and the second law. For years, he tirelessly attempted to derive such a law using classical tools. His intention was not to subvert physics, but rather to salvage it. By 1899, he had formulated an equation that seemed to fit the experimental data, but only by resorting to assumptions that felt rather contrived and ad hoc. The data itself resembled a complex mountain range, and Planck was diligently searching for a path that would lead him through it. His sense of intellectual integrity was uncompromising. He refused to celebrate a formula unless he could justify it on a fundamental level. It was at this juncture that Planck began to sense the ground beneath him giving way. The second law, the bedrock of his intellectual formation, was leading him towards an answer that classical continuity couldn't provide. Part 1 concludes here, at the precipice of Planck's defining struggle, a conservative, law-abiding physicist confronted by a rebellious set of experimental observations. He doesn't yet realize that the solution will necessitate a radical leap, one that will quietly unlock the door to quantum theory. However, he can already sense that something is on the verge of either breaking down or being reborn. Part 2 will delve into that pivotal moment, the night Planck committed what he termed an act of desperation, introduced energy quanta, and unintentionally set in motion a revolution he never intended. As the 20th century dawned, Max Planck found himself in an unusual position. A scientist of conservative inclinations, standing at the edge of crisis he didn't fully accept. In his view, classical physics wasn't a fragile edifice. Rather, it was a well-constructed house. If something seemed amiss, such as blackbody radiation's refusal to conform to established rules, the error, in his estimation, must lie within our calculations, not in nature's inherent continuity. Planck held a deep affection for continuity. He valued clean logic, and he revered the second law of thermodynamics, almost as a musician cherishes a perfect chord. It was for these reasons that his journey to the quantum realm was not a triumphant march of rebellion, but a protracted, hesitant stumble. In 1900, the experimental data concerning blackbody radiation reached a level of precision and obstinacy that could no longer be disregarded. The curve ascended gently at low frequencies, peaked, and then tapered off at high frequencies. Existing theories could only account for portions of it. The Rayleigh-Jeans law aligned with the low-frequency region, but predicted infinite energy at the high end. Wien's law matched high frequencies, but faltered at low ones. The spectrum was akin to a bridge, and classical physics lacked the means to span it. Planck's initial approach relied on the principles he trusted most: thermodynamics. He sought to derive the radiation law from considerations of entropy. He believed that if radiation existed as an equilibrium system, its entropy should be expressible in a manner that yielded the correct energy distribution. Gradually, he refined an expression that accurately fit the entire curve. The formula worked, but he couldn't explain why. And for Planck, merely working was insufficient. He needed a foundation that felt logically inevitable. Consequently, he undertook what he later described as an act of desperation. Planck imagined the walls of a blackbody cavity lined with minuscule oscillators, idealized charged particles capable of absorbing and emitting electromagnetic energy. This model wasn't novel in itself. What was new was what he did to make it produce the correct spectrum. To enumerate the ways in which energy could be distributed among these oscillators, Planck borrowed a statistical method from Boltzmann, the very style of thinking he had resisted for years. And then he did something that, in his own mind, was not a philosophical declaration, but a purely mathematical maneuver. He posited that energy could only be exchanged in small, discrete packets. He called these packets energy elements. Each element possessed a size proportional to the oscillator's frequency, E equals h nu. The constant h, later christened Planck's constant, was not intended as a revolutionary manifesto. It was simply a number that made the accounting work. With that assumption, the entropy calculations suddenly aligned cleanly. And on December 14, 1900, Planck presented his new radiation law to the German Physical Society. The formula harmonized seamlessly with data across the spectrum. The ultraviolet catastrophe vanished. Nature snapped into place as if the universe had been awaiting this slight adjustment in its grammar. But here's the subtle irony. Planck didn't believe he had unveiled a new physics. He thought he had discovered a clever way to rescue the old one. He initially believed that quantization was merely a kind of bookkeeping device, useful for calculations, but not necessarily reflective of reality. In his heart, he still yearned for a continuous world. Yet the constant h was like a seed falling on fertile ground. Even if Planck didn't fully appreciate it, the landscape had begun to change. Over the ensuing years, Planck refined his work, defended it against criticism, and endeavored to interpret the true meaning of quantization. Some colleagues were polite, but skeptical. Others were outright dismissive. The scientific culture of the time remained deeply rooted in classical principles. The notion that energy might not flow smoothly, but in discrete jumps felt like heresy. Then, in 1905, a young patent clerk in Bern employed Planck's trick to explain something Planck himself had hesitated to address. Albert Einstein proposed that light itself came in quanta, later termed photons, to explain the photoelectric effect. Where Planck had quantized the exchange between matter and radiation, Einstein quantized radiation itself. To Planck, this was far too radical. He admired Einstein's brilliance, but he resisted the photon idea for years. Even so, he supported Einstein's career, helped him gain recognition, and invited him into the scientific establishment. Planck's conservatism did not preclude generosity. He could vehemently disagree with an idea while still championing the mind behind it. The quantum revolution was now accelerating beyond Planck's comfort zone. By 1911, the first Solvay conference gathered the world's leading physicists, all grappling with the same unsettling questions. Planck attended as a respected elder. Even though he was barely past 50, the atmosphere was electric. Classical certainty was dissolving, but no new comprehensive framework had yet emerged. Planck listened intently as others extended quantization into new realms. Einstein, Nernst, Poincaré, and later Bohr. He was both proud and uneasy. He had opened the door, but he didn't entirely approve of the room that lay beyond it. Yet Planck's own standing continued to rise. In 1908, he became permanent secretary of the Prussian Academy of Sciences, a role of immense prestige. In 1912, he was appointed professor at the University of Berlin, one of the highest chairs in German science. His lectures were calm, structured, and morally serious. The kind of teaching that made students feel physics was not just a craft, but an ethical pursuit. In 1918, the Nobel Committee awarded Planck the Nobel Prize in Physics for the discovery of energy quanta. The award was late compared with the shockwave he had launched, but it carried a deep symbolic weight. The world was acknowledging that the House of Classical Physics had needed a new pillar after all, and that Planck had provided it. Personally, these were also years of quiet happiness shadowed by growing darkness. He and Marie had children and built a life of music and order. But Europe was sliding toward violence. World War I erupted in 1914, and Planck, like many German intellectuals of his generation, initially signed patriotic declarations in support of his country. He was not a nationalist fanatic. He was a man shaped by loyalty to institutions and by a belief that Germany represented high culture and rational progress. The war, however, shattered that illusion. As bodies piled and empires shook, Planck saw the moral limits of his earlier faith in state wisdom. After the war, Germany collapsed into the Weimar Republic. Fragile, experimental, humiliated by the Treaty of Versailles. Planck was no politician, but he became a guardian of German science in a time of scarcity and bitterness. As a leader in the Kaiser Wilhelm Society, later Max Planck Society, he protected research institutes, advocated for scientific autonomy, and tried to keep German physics connected to the international community even as resentment rose at home. The same temperament that had resisted quantum leaps now served him in public life. Patience, discipline, and a refusal to surrender to despair. Part 2 ends in this dual reality. Planck had become the father of a revolution he barely intended, watching younger physicists carry quantization far past his own imagination. At the same time, he is moving through a Europe whose political ground is turning unstable beneath his feet. His scientific legacy is growing wider every year, but his personal world is about to face tragedies that no equation can soften. Part 3 will follow the next chapter. Planck's later scientific role during the rise of Bohr and the new quantum mechanics, and the devastating private losses and moral trials that came with Germany's descent into Nazism. By the early 1920s, Max Planck was an elder statesman of physics, though he wore that role with the same quiet modesty he had always carried. The quantum revolution he had unwillingly started was now racing beyond him like a river after the ice breaks. Planck did not try to stop it. He didn't even try to claim it. He did something subtler and, in its own way, braver. He became a guardian of the scientific space in which younger minds could argue freely. The younger minds were extraordinary. Niels Bohr was building his atomic model, placing quantized orbits into the heart of matter. Einstein kept disturbing the field with sharp objections and new ideas. Across Germany and Denmark, a generation of physicists began using Planck's constant as a key that unlocked door after door. To Planck, some of their conclusions felt unsettling. He still believed nature was orderly in a classical sense, still wished the statistical interpretation were not the final word. Yet he recognized that a theory's truth is not decided by taste. The facts were pulling physics into a new geometry. In those years, Planck remained intellectually active. He worked on the foundations of thermodynamics and on the meaning of physical law, writing essays that sought unity rather than novelty. He was fascinated by the philosophical implications of quantum ideas, while remaining personally cautious about their most radical interpretations. That tension made him a bridge figure. He could speak to the older classical generation in their language, and to the new quantum explorers without dismissing them as reckless. In scientific culture, bridges matter. They keep revolutions from turning into civil wars. But while physics accelerated, Planck's private life began to fracture. In 1909, his first wife Marie had died suddenly, leaving him with children who needed a father as much as they needed the household order she had held together. He remarried in 1911 to Marga von Haslin, who brought warmth and steadiness into the family again. Yet the tragedies kept coming. One of their daughters died in childbirth during World War I. Another son was killed at the Battle of Verdun. Loss arrived not as a single storm, but as a slow, repeated erosion. Planck, who had always trusted the rational order of nature, now had to live inside a human world that refused to be rational. He did not collapse. His temperament would not allow it. He turned grief into discipline, leaning even more heavily on work, music, and a kind of stoic faith that life demanded endurance even when it offered no explanations. Friends described him as dignified in sorrow, never theatrical, never bitter, yet visibly older after each blow. The quietness that made him strong also made his suffering almost invisible to outsiders. Germany's political atmosphere in the 1920s mirrored that sense of fracture. The Weimar Republic was a fragile attempt at democracy built atop humiliation, inflation, and social resentment. Planck was not an activist, but he was not indifferent. He believed Germany needed stability, lawfulness, and cultural dignity. He feared extremes on both sides, especially anything that threatened intellectual freedom. In his mind, science was one of Germany's remaining moral resources, and protecting it was a form of patriotic duty. As president of the Kaiser Wilhelm Society, Planck spent much of the decade doing exactly that, raising funds, shielding institutes from political meddling, rebuilding international ties after the war. He traveled, lectured, and corresponded with scientists abroad, trying to stitch German research back into the global fabric. The irony was sharp. The man who had changed physics through a desperate mathematical trick now spent his public life trying to keep Germany from changing politically through desperate ideologies. By the late 1920s, quantum mechanics had reached a second, even more radical phase. Werner Heisenberg's matrix mechanics and Erwin Schrödinger's wave mechanics emerged in 1925 to 26, and soon were shown to be two forms of the same, deeper theory. The old world of definite trajectories dissolved into probabilities and wave functions. Bohr's Copenhagen interpretation insisted that uncertainty was not a limitation of our instruments, but a basic feature of reality. Planck watched all of this with admiration and unease. He did not oppose quantum mechanics. He accepted its mathematical success, but he struggled with its philosophical tone. The universe he had loved for its absolutes was now presented as a field of tendencies, where measurement played a mysterious role. Still, he supported the new generation. He encouraged Heisenberg. He respected Schrödinger. He was proud that Germany, despite political chaos, remained a center of theoretical physics. When young scientists visited his office in Berlin, they found a man who listened carefully, asked precise questions, and argued with the gentleness of someone who wanted truth more than victory. If Planck had a legacy besides his constant, it was the moral style of his scholarship. Then, in 1933, the ground under everything shifted. Adolf Hitler rose to power, and with him came a regime that treated independent thought like an enemy. Universities were purged. Jewish scientists were fired or forced to flee. The state demanded ideological loyalty from research institutions. For German science, it was a hemorrhage. For Planck, it was heartbreak. He was already in his 70s, and his instinct was not rebellion, but preservation. He believed the best way to save German science was to keep it alive inside Germany until the nightmare passed. That meant negotiating with a regime he despised. Planck met Hitler in 1933, hoping to argue that the dismissal of Jewish scholars would destroy Germany's intellectual future. The meeting was a failure. Hitler ranted about race and treason, and Planck left understanding that rational argument had no power here. What did he do after that? He did what a cautious moralist does in a collapsing world. He tried to hold small lines even when the big ones were lost. Planck did not publicly denounce the Nazis, partly from fear, partly because he believed open confrontation would only accelerate destruction. But he also did not cooperate in spirit. He used his authority in the Kaiser Wilhelm Society to delay dismissals where he could, to protect individuals in quiet ways, to keep institutes functioning without turning them into propaganda machines. He corresponded discreetly with colleagues who were leaving Germany, expressing sorrow and admiration. He helped some secure positions abroad. History sometimes judges such restraint harshly, but for Planck it was a strategy of survival for both people and institutions. Even this strategy had limits. The Nazis tolerated Planck because of his age, prestige, and because they liked displaying famous Germans as proof of national greatness. Yet they also watched him. Friends warned him to be careful. He kept giving lectures that avoided politics, speaking only of science and culture, as if insisting that within the darkness there must remain a small republic of reason. Around him, German physics split. Some embraced the regime, preaching Aryan physics and attacking relativity and quantum theory as Jewish. Others retreated into silence. Planck tried to protect the integrity of the discipline, but he was fighting a tide that had no respect for integrity. At home, tragedy returned again. His son Erwin, a civil servant with conservative values, became involved in resistance circles that later supported the July 20th, 1944 plot against Hitler. In the 1930s, Planck already sensed the danger his son was walking toward, though the full scale of what was coming could not yet be known. The family lived with quiet fear. Love for country tangled with horror at what the country had become. Part 3 ends in that shadowed decade. Scientifically, Planck has lived to see quantum mechanics become a full architecture of reality, beautiful, strange, and forever tied to his constant. Personally and morally, he is living to the collapse of the Germany he once trusted, trying to defend science without surrendering to a regime he cannot stop. The man who once believed in absolute laws has learned that human history is not absolute at all. It is fragile, and sometimes cruelly irrational. Part 4 will follow the deepening of that tragedy. The war years, the loss of his son, the destruction of Berlin, and Planck's final attempt to salvage meaning and the future of German science from the ruins. The 1930s turned into the 1940s, like a door closing slowly, but with a sound that never stopped echoing. Max Planck was now an old man in a young century gone mad. He had lived through the birth of quantum theory, through the collapse of an empire, through Weimar's fragile hopes. Yet nothing prepared him for what Germany became under Nazi rule. The state that once celebrated universities as temples of reason now treated reason as a threat. Planck watched friends vanish from lecture halls, dismissed, humiliated, exiled for being Jewish, or simply for refusing to kneel. He saw institutes drained of brilliance, not by scientific error but by ideology. Planck had tried to resist in the only way he believed might help. Quietly, institutionally, with a slow pressure prestige rather than the hot spark of confrontation. He had met Hitler in 1933 and left defeated by the ugliness of a mind unreachable by argument. Since then, he had chosen survival as a moral strategy, holding together the Kaiser Wilhelm Society as a shelter for research, delaying dismissals where possible, insisting on scientific standards when the regime wanted slogans. But by the early 1940s, even that shelter felt like a paper roof in a storm. War made everything. Worse still, Germany's conquest of Europe transformed Berlin into the nerve center of a monstrous machine, one that systematically extinguished millions of lives. As Allied bombs began to rain down on German cities, Planck's existence was reduced to two desperate spheres: the realm of science he fought to preserve, and the safety of his family, which he tried desperately to guarantee. Tragically, one of these circles would collapse before the other. In February 1944, an Allied air raid reduced Planck's Berlin home to rubble. The very building that houses invaluable papers, his correspondence with the pioneers of modern physics, his notes chronicling decades of groundbreaking thought, everything was wiped out in a single devastating night. This was more than a mere loss of property. It felt like a symbolic obliteration. Planck, a man who had always revered order and structure, now stood amidst the ruins of his own intellectual history. Friends who witnessed the scene recalled that he didn't break down in wails or fits of anger. Instead, he simply appeared older, as if a stark realization had finally taken root within him, that the brutality of human violence can incinerate even the most carefully constructed life, reducing it to ashes. Following the bombing, Planck and his second wife, Marga, sought refuge in the countryside near Magdeburg. While the rural tranquility might have provided some solace, it also ushered in a new and ominous peril. The war was reaching its catastrophic climax. Allied armies were relentlessly advancing from both the west and the east, and the relentless front line swept through villages like encroaching shadows. An 86-year-old Nobel laureate, a giant in his field, was now a displaced person in his own homeland, passively awaiting the final, devastating act of history. Then came a blow that shattered more than just physical structures. In July 1944, a courageous group of German officers and conservatives launched a daring attempt to assassinate Hitler, Operation Valkyrie, the infamous July 20th plot. Among the network of resistance fighters was Planck's own son, Erwin, a dedicated civil servant who had become deeply involved in clandestine anti-Nazi circles. Erwin was apprehended on July 23rd. The infamous People's Court swiftly condemned him to death in October, staging a sham trial designed to terrorize the populace as much as to punish the accused. Max Planck, driven by paternal instinct, did what any father, and perhaps only a father, could possibly do in that desperate situation. He penned a personal letter directly to Hitler, pleading for Erwin's life. The letter was characterized by its dignified tone, avoiding any political arguments and focusing instead on a heartfelt plea for mercy. Tragically, it was completely ignored. On January 23, 1945, Erwin Planck was executed by hanging at Plötzensee prison in Berlin. Erwin's death left an emptiness within Planck that eclipsed even his earlier profound losses. He had already faced the unbearable pain of burying children. 2 daughters, a son lost of Verdun, and another claimed by the perils of childbirth. But Erwin held a unique place in his heart. He was a child closest to him, the one with whom he shared daily conversations and who embodied the family's unwavering moral compass. Friends who knew him well observed that after January 1945, Planck's very will to live seemed to fracture. He didn't succumb to dramatic displays of emotion. Instead, he retreated into a quietness that was profoundly unsettling, as if the last fragile thread connecting him to Germany's future had finally been severed. And yet, even in the depths of his grief, he remained the quintessential Planck, disciplined, morally upright, and resolute in his refusal to let despair serve as an excuse for surrender. When the war finally ended in May 1945, Germany lay in ruins, a landscape of devastation. Institutions had crumbled. Cities were reduced to skeletal remains, and trust had utterly evaporated. Planck, now 87 years old, was taken into the care of Allied forces and brought to Göttingen for his safety. For another man of his advanced age, this might have signaled a retreat from public life, but for Planck, it sparked the opposite reaction. He firmly believed that Germany's salvation, if such a thing were even possible, lay in painstakingly rebuilding the moral and intellectual foundations that Nazism had so ruthlessly sought to destroy. For him, science was far more than just a profession. It was a vital pathway for a nation to reclaim its dignity without resorting to violence. And so, astonishingly, he returned to institutional leadership. In 1945-46, he once again served as president of the Kaiser Wilhelm Society, collaborating with esteemed colleagues like Otto Hahn to reorganize German research under the watchful oversight of the Allied forces. The society itself would soon be renamed the Max Planck Society, both as a fitting tribute to his contributions and as a clear declaration that German science was determined to begin anew on a foundation of intellectual and moral purity. While Planck's age and physical frailty prevented him from designing this new order single-handedly, his very presence held immense significance. He served as a living testament to the fact that German thought possessed a heritage far deeper and more enduring than the insidious ideology of Nazism, and that renewal was indeed possible without erasing the memory of collective guilt. Physically, however, he was visibly fading. The relentless pressures of the war years had taken a heavy toll on him, and Erwin's tragic death had irrevocably damaged his spirit. Yet those who visited him in Göttingen found a man whose mind remained remarkably sharp, still capable of discussing physics with unwavering clarity, and still finding solace in playing simple pieces of music on the piano whenever his hands allowed. Music remained his steadfast refuge. Even if he could no longer exert control over the course of history, he could still find moments of harmony, however fleeting, in the realm of music. In his conversations, Planck rarely spoke about the quantum revolution anymore. He had long since accepted that younger, more energetic minds would carry that torch forward. His thoughts now gravitated toward more fundamental themes: ethics, responsibility, and the inherent fragility of civilization. He had witnessed firsthand the collapse of a nation, not due to ignorance, but as a result of moral decay. This profound lesson weighed heavier on him than any complex equation. On October 4th, 1947, Max Planck passed away peacefully in Göttingen. His final years have been defined not by scientific breakthroughs, but by his remarkable resilience and enduring spirit. In the quiet solemnity of his death, Germany's scientific community mourned not only the loss of a founding father of quantum theory, but also the departure of a shining example of how to remain human in the face of monstrous historical forces. Part 4 concludes with Planck standing at the intersection of two sets of ruins, the war-torn landscape of Berlin and the shattered moral landscape of his nation. He did not live long enough to witness Germany's full recovery. However, he lived long enough to sow the seeds of renewal, seeds rooted not in ideology, but in the unwavering and patient pursuit of truth. Part 5 will delve into the lasting impact of his legacy, how his constant reshaped the field of physics after his death, how the Max Planck Society evolved into a global powerhouse of scientific research, and why a man who introduced quanta with such reluctance ultimately came to symbolize the courage to begin anew, even in the face of unimaginable adversity. When Max Planck died in 1947, the world he left behind bore little resemblance to the one he had entered as a shy and unassuming student in Munich. In his youth, physics had seemed like a near-perfected cathedral. Solid walls built upon the foundations of Newton, Maxwell, and classical certainty. By the time he closed his eyes for the final time, that cathedral had been completely rebuilt from the inside out. It stood taller, more enigmatic, and filled with chambers that no one in the 19th century could have ever conceived of. Yet, in nearly every one of those chambers, one could find a small but significant inscription written in the language of equations. H. Planck's constant was no longer simply a numerical value used in a single, desperate calculation. It had become a fundamental boundary marker of reality itself. The scale at which the universe ceases to behave like a smooth, continuous river and begins to exhibit the characteristics of a discrete, mosaic-like structure. By the late 1940s, quantum mechanics was already profoundly influencing how scientists approached the study of atoms, chemistry, and light. In the decades that followed his death, it would come to shape everything from transistors to lasers, from nuclear power to the GPS signals that silently guide airplanes across the globe. Planck's most famous act had been undertaken with reluctance, almost accidentally, yet the reverberations of that act ultimately shaped the very architecture of modern technology. What makes this legacy particularly poignant is the striking contrast between Planck's personal temperament and the revolutionary changes he unleashed. He never consciously aspired to be a prophet. His deepest desire was to safeguard the established order of physics, not to dismantle it. He was, at heart, a man of continuity who inadvertently discovered discontinuity. He harbored doubts about statistical interpretations, yet he unlocked the door for probability to become the very grammar of nature. If history tends to favor heroes who exude boldness, Planck was bold in a profoundly different way. He possessed the intellectual honesty to accept answers that clashed with his own personal philosophical inclinations. In the aftermath of the war, the institutions that Planck had so diligently protected through decades of turmoil found themselves in need of a radical transformation. The Kaiser Wilhelm Society had flourished under the German Empire, survived the Weimar Republic, and been distorted under the oppressive rule of the Nazi regime. In 1948, 1 year after Planck's passing, it was officially reestablished as the Max Planck Society for the Advancement of Science. The name was far more than a simple act of commemoration. It was a clear and unequivocal statement of intent. German science would rebuild itself on a bedrock of truth-seeking rather than ideology, and would do so under the enduring moral influence of a man who had striven quietly and steadfastly to keep the flame of reason alive in an age defined by unreason. The Max Planck Society experienced rapid growth in the post-war years and eventually emerged as one of the world's preeminent research networks. Its various institutes have been responsible for groundbreaking discoveries in physics, chemistry, biology, medicine, and the social sciences. To this day, the Society's culture reflects many of the values that Planck himself embodied: rigorous standards, international collaboration, and a firm conviction that science can only thrive when it is shielded from the corrupting influence of political extremism. The Society's success has added another layer to Planck's multifaceted legacy. He not only revolutionized physics, he became a symbol of how to rebuild science after a period of moral collapse. Yet, Planck's story doesn't simply conclude in the confines of laboratories and research institutions. It finds its ultimate expression in the way people choose to remember him. In the collective public imagination, Planck is often hailed as the father of quantum theory. While this label is undeniably accurate, it tends to obscure a subtle nuance. Most fathers actively envision their child's existence long before it is born. In Planck's case, quantum theory was more like a child born out of sheer necessity, then adopted by a larger community of brilliant thinkers who nurtured it into adulthood. Einstein, Bohr, Heisenberg, Schrödinger, Bohr, and Dirac. Each of these scientific luminaries took the seed that Planck had planted and cultivated into a sprawling and vibrant forest. Planck himself sometimes felt uneasy about certain aspects of that forest. He did not necessarily embrace every interpretation that quantum theory took, but he never entertained the thought of setting the forest ablaze. He understood that discovery ultimately belongs to reality itself, and only secondarily to the individual who makes the initial discovery. This particular attitude is crucial because it reveals the very essence of his moral character. In a century that often rewarded ostentatiousness and self-promotion, Planck was a man of quiet principle. He didn't build his career through theatrical displays or the cultivation of a personal cult of personality. He built it through unwavering attention to what the evidence demanded. The very same unwavering dedication guided him through the darkest periods of political turmoil. He was not a heroic resistor in the mold of a cinematic protagonist, but he accomplished something that is often difficult to capture on film. He protected individuals and principles through patient, often risky, perseverance. He endeavored to keep Jewish colleagues employed for as long as humanly possible. He strove to prevent German science from becoming a mere propaganda tool. While he was ultimately unable to halt the destructive machinery of a Nazi regime, he succeeded in leaving behind a legacy of integrity that later generations could trace back to his unwavering example. And perhaps the most poignant aspect of his legacy is the lesson that can be drawn from his profound grief. Planck endured the loss of his first wife, 2 daughters, and 2 sons. The final blow, the execution of Erwin, arrived when he was far too old to rebuild his shattered personal world. In individuals of lesser character, such a series of devastating losses might have given rise to bitterness, cynicism, or a retreat into a form of faith that sought to deny the harsh realities of the world. Planck's response was marked by neither denial nor rage. It was characterized by endurance. He continued to play the piano between air raids. He continued to speak about truth and responsibility even as his country descended into moral toxicity. He maintained his belief in the existence of order, even after disorder had taken nearly everything he held dear. In that sense, Planck's constant serves as an apt, if unintentional, metaphor for his character, a small, unchanging value that persists even as the universe around it becomes chaotic and unpredictable. Why is this particular aspect of his story relevant to the narrative of quantum physics? Because the quantum world can often seem impersonal and cold if it is presented solely through the lens of mathematical formulas. Planck's life provides it with a human face. His story illustrates that revolutions can arise from reluctant individuals, that humility can serve as a powerful engine of historical change, and that one does not need to crave destruction in order to bring something new into existence. Sometimes, the most profound changes begin as a carefully considered attempt to preserve what we cherish most. By the time Planck was gone, quantum theory had become an unstoppable force. But in another sense, his life continued to exert its influence on how science itself envisioned its ultimate purpose. He approached physics as a moral craft, seeking to uncover the laws of nature not for the sake of dominance or control, but for the sake of deeper understanding. That ideal survived him. It was passed on to the Max Planck Society. It has become an integral part of the global understanding that science must be international in scope, rigorously skeptical in its methods, and fiercely independent in its pursuit of knowledge. And so, Part 5 leaves Planck not in the midst of a dramatic finale, but in the quieter realm of enduring continuity. The elderly man who had once viewed quantization as a mere computational device ended up providing the modern world with an entirely new lens through which to perceive reality. He did not choose revolution as a matter of personal ambition. He chose truth as a matter of unwavering discipline. And as a direct result of that choice, the universe now speaks, in part, in his name, Whenever a photon is counted, an electron is guided through silicon or assigned to stand before an unexpected curve and decides, however reluctantly, to follow where it ultimately leads.